All right, everybody, here are the free response questions from the AP Physics 1 2026 exam. Let's just go ahead and jump right into them. The first question that we have here is a water fountain. You have the water is actually going in projectile path, and essentially we want to, of course, answer some questions about it. So we've got a height, we've got an angle, and part A, we're asked to sketch the graphs for the horizontal and vertical components of the velocity. That's not too bad. It's in projectile motion, only has acceleration due to gravity, so we should be having two graphs that look like this. One to indicate 0 horizontal acceleration, one to indicate a constant vertical acceleration. That's pretty easy. Second part, we have to derive an expression for the speed of the water after exiting the nozzle. For this one, I think I'm going to actually use kinematics because I think that'll be easier in terms of just thinking about height and angle. What we do know is we do know that this water does go up to a height of h1. So I'm going to say Vf squared equals V naught squared plus 2a delta x. Plugging in our values, we've got 0 for the vertical velocity at the top. That should equal V0 squared times sine squared of theta 0 minus 2g h1, because that's how high the water goes. Of course, we only care about just the vertical component of velocity. So we can easily solve that. You get v0 is equal to 2g h1 square root, all divided by just sine of theta 0. The nozzle has a cross-sectional of radius r0. It's a circle. You want to find volume flow rate. That's easy. It's just equal to AV. And so that's just going to be equal to pi r0 squared times root 2g h1 divided by, sorry, not dividing the square there. That's an r0 squared, root 2g h1 over sine of theta 0. Not too bad. All right, new fountain is present with a smaller radius, and we're asked how the height will change if you have the same volume flow rate. The new one should have a higher height. We can say since both fountains have the same volume flow rate, then that implies that fountain 2 has a bigger speed due to a smaller area. Since the water is shot up at same angle and still in free fall once it leaves the pipe, H2 must be greater than H1. Notice that it's beyond mathematical expression, so we can't use A1V1 equals A2V2 as like our full reasoning for this. So it has the same angle. Since it's still in free fall, that means it's going to have the same acceleration in both cases as well. All right, question 1 done. I'm just trying to go through these kind of fast right now because my voice is not really doing too hot right now. Don't know whether I've been talking too much this week or if I'm getting sick or what. Hopefully it's not the latter, but in any case. All right, collisions question. We're told after the collision, disk R moves with a speed of v0 over 2 in the negative x direction, and then we're going to want to draw both of the momenta as a function of, not as a function of anything actually, just after the collision. We're given the two before. Make note that disk R has 4 tick marks for the arrow, and of course disk S being at rest has 0. After the collision, we have to actually figure out the momentum vectors. Well, disk R should only have 2 tick marks because it's at half its initial speed. Disk S should have 6. We know that because total momentum must still be conserved. Go back over here. 4 and 0 gives you a total of 4. 2 and then negative 2 and 6 gives you a total of 4. So that works out quite nicely. All right, starting out with conservation of linear momentum, derive an expression for the kinetic energy of just disk S after the collision. So I'm going to start with Pi is equal to Pf for total momentum, right? So then that tells you that M0 V0 is equal to M0 times negative V0 over 2 plus 3M0 times its final velocity for disk S. That means that disk S has a final velocity of just positive v0 over 2. Well, kinetic energy is equal to a half times the mass times speed squared. So you're going to have a half times 3m0 times v0 over 2 squared, or 3m0 v0 squared over 8. There you go. Part C, you're asked about the positions after the collision of everything. So I'm going to go ahead, move this over, and we'll go ahead and draw the positions. Well, disk R moved at half its initial speed after the collision. So here's disk R. You do have to label them. Center of mass has a constant speed because there's no external forces. And then disk S has the same velocity and therefore the same slope or magnitude of slope as disk R. So there you go. During the collision, the magnitudes of change in momentum are those, indicate whether they're one of these, they're equal. It's essentially always equal if it's two objects in a collision. So then that's going to give you Newton's third law. We have equal opposite forces for equal time, and we know that F delta T equals change in momentum. That's it. All right, question 3 is our experimental design. You want to find the coefficient of friction given just a meter stick. It's actually not as bad as you might think it is. All you have to do is measure the initial height and the horizontal distance traveled, h and x. That's it. So starting height and horizontal distance traveled. All right, describe a method to reduce experimental uncertainty. We are going to vary the starting height and repeat the experiment multiple times. We'll say maybe 4 or 5 times. There we go. Indicate which quantities could be graphed and then describe a relationship between everything. We are going to graph x on the vertical and h on the horizontal, and then the slope must equal 1 over mu k. Now you might be asking, well, how do you know this just from looking at the question? I've actually solved this exact scenario several times before for x as a function of h and the coefficient of friction. All you actually have to do is just a conservation of energy. All of the initial potential energy must get converted into thermal energy by the time the block stops. So x is h over mu k. Plot x versus h, you're left with the slope, which is 1 over mu k. So that's not too bad then. All right, part C of the experimental design, there seems to be a bunch of stuff with no real numbers, so I don't care about any of that. All I actually care about is the data table, the equation, and the numbers provided, and then what we want to find. You were told that we're given d on the horizontal axis. V is our other variable, which means almost certainly we're going to be plotting v squared. As a matter of fact, we do have to do that. We're going to plot v squared, and that's meters squared over seconds squared for its units. Now, how do I know that to find mu k? Well, again, we have the equation v squared is equal to d, and then you have, whoops, sorry, something just fell in the background, 2g sine theta minus mu cos theta. So if I plot v squared over d, all I'm left with are these constants. We already know what theta is, we know what g is, we can solve for the coefficient using our slope then. How I would scale it, because v squared is going to go up to like 0.27 if you compute all of your v values squared, is I would scale it along the lines like this. You have 6 major grid lines on the vertical axis, so scale it by 0.05s and you'll be fine. Something like that. Of course, you can plot the data, you can draw a straight line through it, you have to, as a matter of fact. I am not going to do that, simply because I don't have the square numbers here, and it's just going to take more time to do it. You guys know how to square values in your calculator, right? You just put them on here, draw your best fit line using a ruler, and you're good. However, I am going to do part D, which says to actually figure out how to calculate the experimental value. Going back to our equation, we have v squared over d, which should equal our slope. So I'm going to write that down. That must equal everything left over here. So that's equal to 2g sine theta minus mu k cos theta. We already know what g and theta are. G is 10 and the angle is 30 degrees. So we have slope is equal to 20 times a half minus mu k times 0.866. And then from that, of course, we can solve for the coefficient. I got a value of around 0.55, but my line was also not perfect when I did it on the side. So it's probably going to be something a little bit higher than that, I would imagine. Yeah, because you end up with mu k equals, let's see, everything's going to be over 0.866. You are going to have, why am I doing this in my head? Times 20, rather. 10 minus the slope, if I'm not mistaken. Does that seem right? Let's see. You move that over, move this over. Yes, 10 minus slope over 20. That is not correct. This should be a half, not 10. 0.5. Yeah, this seems right. Yes, yeah, this is fine. Okay, there you go. All right. Question 4, two tops. You want to essentially figure out who's going to have the bigger inertia once the strings leave the thing. Both of the strings have a length of L0, and the inertia is a half inertia, inertia of y rather is a half of inertia of x. You might think forces, velocity, momentum. Don't do that. You can actually go back here and it'll tell you, starting with the work energy theorem for the derivation, which means you should think about this question from either a torque and acceleration and kinematics perspective or a work energy perspective. So I can, however, say that omega y is greater than omega x. Here's how I'm going to justify it then. Both yo-yos, or tops, or whatever you want to call them, both toys, experience the same torque, and the string is the same length. So they spin for the same angle. Therefore, they have equal work done. So equal changes in energy, in kinetic energy. This means then that since x has a greater inertia, y must move faster. There we go. We can use that to help us solve part B. Part B, we're going to use work equals change in energy, right? Just like it asks us to. That is going to tell you that the torque times the angular displacement is equal to 1/2 times the inertia of x times its final angular velocity squared. Torque is equal to RF, just RF here because there's no angle that we care about. It's going to be R0, F0. Delta theta can be obtained by saying that delta theta is equal to delta x over radius. Well, the length of the string is L0, so your arc length that your yo-yo essentially travels, or rather that the axle travels, is going to be L0. So that implies then that torque, time, which is force, times radius, all multiplied by length over radius, so you're going to have L0, F0, is a half I x omega x squared. So omega x equals square root of all of that once you solve it. So 2L0, F0 over Ix. And then for part C, pretty easy. I'm not even going to write it, but the wording I would say is that it is consistent because the angular velocity depends inversely on the square root of inertia. Since Ix is bigger than Iy, then that implies that omega x must be less than omega y. All right, and that's it for this question. You could solve it with torque as well. If you do solve part B with torque, you would want to use net torque is equal to I times alpha, and then you would want to use that in conjunction with this kinematics equation. I am not going to work through that, but if you use both of these together for the Newton's second law in rotational form, that will allow you to get the same answer for your angular velocity, and I do invite you to check that out and let me know in the comments if you have any questions. But thank you so much for watching, guys, and I hope you have a great day.